Swayam Prabha. Digital India. Educated India.
Okay, so good morning, good afternoon. Welcome back to our series of lectures on analysis and design of rigid pavements. We are almost at the home stretch. We are nearly done with these lectures. We've learned a lot over the past several weeks as we went through these lectures. So let's do a quick recap before going into today's lecture. Let's do a quick recap on where exactly we are in terms of the overall class. So the entire course was divided into 4 modules. Module 1, which was an introductory module. Module 2 was the analysis of rigid pavements using classical methods. Module 3 was the analysis using new modern numerical methods, in particular the finite element method. Of course, this is not a class on the finite element method, so it's not possible to teach you everything over there, and I do encourage you to take a formal class on FEM. But still, I've tried to show you a little bit of the basics and how it can be applied to rigid pavements. And finally, we are in module 4, which is on the mechanistic empirical design of rigid pavements, which is really the modern philosophy of design. It's not the only design, and indeed there are many countries which use different philosophies of design, but the modern philosophy which is used most widely is the mechanistic empirical design philosophy as applied to rigid pavements. Also applies to flexible pavements, but do take a separate class to know more on that. Now, why did we learn it in this order? Of course, the module 1 was just an introduction. The introduction primarily was to explain to you the different types of rigid pavements. So we saw that we have jointed plain concrete pavements, JPCP, jointed reinforced concrete pavements, JRCP. We have CRCP, continuously reinforced concrete pavements. And finally, we had pre-stressed concrete pavements, or PCP. Now, of these, JRCP and PCP were not going to be discussed in this class. JRCP is very rarely used these days, and then PCP is a very specialized application. As of this point, it's probably better learned in structural engineering than in pavement engineering. But what we were focusing on this class was on JPCP and CRCP. Now, of course, JPCP is by far the most commonly used type of rigid pavement. If you go out and you see a rigid pavement, there's a very, very good chance there's going to be a JPCP pavement. CRCP is not unheard of all over the world, including in India. You do have several CRCP sections, but it's just less used, less often used. Mostly CRCP is going to be used on roads which experience very heavy, high volumes of traffic, and that traffic consists a lot of heavy trucks. So those type of pavements where durability over time is a very, very important factor. Typically, those are expressways or major highways which carry very, very important goods traffic. Those are where you would see CRCP. Now, most of the class we did focus on JPCP, but I have shown you that we essentially also considered CRCP at the same time, because as far as analysis is concerned, and we'll talk a little more about analysis in a bit, as far as analysis is concerned, CRCP tracks very closely with JPCP. It's mainly at the point of design that the two branch off, because JPCP design is largely based on cracking as well as faulting. So those are the distresses which are interested in for JPCP. And CRCP design is going to be based largely on punch outs and crack widths for the most part, because those are the sort of things that we are interested in for CRCP. So in terms of analysis, they're very, very similar to each other. In terms of design, they kind of move out and spread out. And I hope in module 4, I had given you a little bit of a hint there. I showed you how in the AASHTO ME, so in the AASHTO ME PDG or AASHTO Pavement ME, which is the most modern and most comprehensive sort of mechanistic empirical design procedure as implemented by any country. This is mostly in the United States and North America. So in that procedure, they do show you that essentially the same sort of analysis method is used for both JPCP and CRCP. It's just that for CRCP, the way to calculate the distresses, which is punch outs and crack width, those vary. We will also see CRCP one more time before we conclude this series of lectures, and that will actually be the last lecture which we go into in this series on IRC. That's when we get to IRC 118. So currently we are looking at the Indian design practice, haven't seen the American design practice, and of course now both of them, for the Indian design and the American design practice, it's not that they're radically different from each other. In the previous lecture, which was lecture 34, I gave you an introduction to the Indian design practice, which is essentially IRC 58. In particular, the latest edition, which is the 4th revision, which is IRC 58 2015. And as we saw in that previous lecture, and if you don't recollect, please go back and review the lecture once. But as we saw in the previous lecture, IRC 58 2015 is a very modern mechanistic based design, and it follows many concepts which are used in the MEPDG. Indeed, if you, as I showed you in the previous lecture, if you actually look at the list of acronyms which are mentioned at the beginning of the document, they do actually mention what is MEPDG, what is NCHRP. So you'll find many references to AASHTO, MEPDG and NCHRP in the document itself. So they've been pretty thorough in terms of collecting scientific literature and using the latest concepts. There are some critical areas where there is divergence. One of them we'll actually learn about today. But before we go into today's lecture, I just wanted to remind you a little bit on analysis and what we've been doing for analysis so far. Now, analysis, at the end of the day, very simplistically put, when we're talking about analysis of rigid pavements, what we basically mean is if you place a load on a JPCP or a CRCP, then can you calculate the stresses, the critical stresses, strains, as well as displacements under that load? That's basically what we mean by analysis. From that, then we can go on and further do our design. And as I had emphasized at the beginning of module 4, the mechanistic empirical design concept is an iterative design concept. That means we start with the trial design, we do certain calculations, we calculate stresses, strains, deflections. We calculate, for example, fatigue damage. That's the mechanistic part of it. The empirical part of it is then we go on to relate the fatigue damage to some amount of design, and then we check whether that final fatigue damage with an amount of reliability added to it, that the amount of distress with certain amount of reliability added to it, whether that exceeds a threshold or not. And that threshold is a policy-based decision. There's not much engineering guidance on that threshold. If it does exceed that threshold, then we consider that to be a failed design. We have to go back, we have to update our trial section. And I showed a couple of lectures ago that even updating the trial section is not a very straightforward thing. AASHTO MEPDG does it in a very simplistic direct search algorithm where they essentially only change the thickness of the surface layer, but you have many more options, and it's actually computationally quite challenging to be able to explore all the available options to the designer. But anyway, you go back and update the design and repeat the entire analysis, and you keep doing this until your calculated distresses are below the allowable maximum value of the distresses. So the reason we spent so much time on analysis in this class was really because modern design is an iterative process. So it's very important that you are very comfortable and very solid in being able to perform analysis of JPCP. Without that, you wouldn't be able to perform a design of JPCP, and same for CRCP. So within analysis then, we had two whole modules. Module 2 was on classical methods, Westergaard's theory, Freiberg's theory, and various variations of it, all of which gave us some nice closed form solutions. But those solutions were built under a series of assumptions, some of which were a bit excessive and lead to severe over or underestimation of the structural response of the pavement. As I mentioned, one of the biggest assumptions there is the so-called infinite slab assumption. That is, the load, wherever the load is placed, either if it's placed near a joint or if it's placed in the middle of the slab, all the other joints are very far away from the load, and therefore they don't really affect the development of stresses or structural responses under that load. That's a very major restriction, and as we saw in some of the figures which I showed you back then, and please review those lectures if you want a refresher, as I showed you over there, it can lead to severe overestimation of stresses if you have such large slabs. There were also several other shortcomings. I won't repeat them, but we had discussed them several times. And it's because of these shortcomings, as well as the development of modern digital computers, that from the 1990s onwards roughly, in pavement engineering, the concept of using the finite element method in rigid pavements, the finite element method has become very popular. FEM is a numerical method where, first of all, we already know we're going to get an approximate solution. So in analytical methods, under a series of assumptions, we are trying to pinpoint a certain correct value such that there is no error in the value as long as the assumptions made were correct. In the finite element method, we straight away begin with the idea that we are going to get an approximate solution. It's really a different way of thinking altogether. If you pause and think about it, that's not how you solve problems. You don't solve problems assuming you're going to get a wrong answer. But in FEM, we do solve problems assuming our problem is approximate, which is a way of saying wrong, but not very wrong. So it's approximate, but in such a way that but it's convergent. That means if we keep increasing the number of elements, then hopefully a solution will basically reach the correct solution within a very small amount of error. And that error is generally tolerable because we do have some amount of variance in construction and some amount of variance in practice. So even if our design has a little bit of variation and construction also a little bit of variation, it's not much of an issue in both of these cases. In some cases, they might cancel each other out due to their randomness. All right. So in the mechanistic empirical design, modern concepts of ME design, we used the finite element method for the analysis. Now within the finite element method, we looked at the MCZ plate theory as well as certain theories for dowels, in particular the dowel component model. Those are all used in ASH2ME. So I hope from those two lectures you became very comfortable in doing the analysis of rigid pavements, in particular JPCP. Now, once we came to module 4, we started by explaining the philosophy of mechanistic empirical design, which I just mentioned. Mechanistic part is for a certain trial section, for certain combination of loads, which we call the axial load spectrum, for certain climatic conditions, and that's actually going to be the main topic of today's lecture. For certain climatic conditions, we calculate what are the stresses for rigid pavements. From the stresses, then we calculate what is the fatigue damage, combining stresses and traffic repetitions. We calculate what is the fatigue damage. That's the mechanistic part of it. So as long as we're calculating fatigue damage, it's a mechanistic design. The failure criteria could stop at that. Our failure criteria could be at fatigue damage. Generally, we assume that total fatigue damage or cumulative fatigue damage is equal to 1. That's Miner's hypothesis. Or the philosophy of ME design is to go one step further, that instead of using fatigue damage, which at the end of the day doesn't really mean much, it's just a mathematical concept. To a pavement engineer, you can't really measure fatigue damage per se. So instead of using fatigue damage as the final failure criteria, the ASH2ME PDG goes one step further. It relates the fatigue damage to a certain amount of observed distresses. Those observations are made in in-service pavements. There's no need to create specialized test tracks as was done in the ASHO road test, which was used in the empirical design guide. These are data collected on existing roads. They can be updated relatively easily. Indeed, you do get regular updates to these functions. And these functions which convert fatigue damage to distress are called transfer functions. So we saw in the ASH2ME PDG, we saw this entire concept. We saw various ways in which stresses are calculated. From stresses, how the response is calculated, and then how fatigue damage is calculated. And then we looked at a number of different transfer functions. And indeed, at this point, there are probably hundreds of transfer functions because you keep having local calibrations and there's a variety of sophistication that can be done in these statistical models. So I just showed you a little bit of what's used in ASH2ME. It doesn't mean those are the only ones available. So what we saw in ASH2ME, to conclude for ASH2ME, is then these transfer functions are used to calculate distresses, and then the whole process repeats. Are distresses less than allowable limit? If yes, then it's an accepted design. If no, then the trial section has to be updated. So that's what we looked at for a large part of module 4. Now coming to the rest of module 4, in the previous lecture, I gave you an introduction to IRC 58. So IRC 58 is the standard code of practice for design of rigid pavements in India, and I gave you a brief overview of the different attributes or the salient features of IRC 58. And as you saw, that a lot of the concepts we learned for ASH2ME PDG actually come back in IRC 58 also. So a lot of ideas, a lot of philosophies also exist in IRC 58. But as I had mentioned back then, there are certain major deviations in terms of how the two approach different problems. So they both tackle the same problems, but the approach is notably different in certain cases. One of those cases is going to be the topic of today's lecture, which is climate effects. So we had a lot of discussion. So way back in module 2, as well as again in module 4 in the MEPDG part, we talked about what are the effects of climate, how do you characterize climate, and how do these climatic variables or meteorological variables, how do they affect the performance of rigid pavements. We talked about generally how it's done. We talked about how it's implemented in ASH2ME. In particular, if you recall, in ASH2ME PDG, there is the EICM, the Enhanced Integrated Climatic Model, which actually calculates temperature distributions. Then there is separate consideration for built-in curling, where basically just one number, which is 5.6 degrees Celsius, one number is taken as sort of the default built-in curling value, although there's quite a lot of controversy over that value. And then there is also some consideration of shrinkage, which is just done through, I have shown the symbol to you, TSH. So basically shrinkage, we turn into some sort of fictitious temperature distribution. It's not a real temperature distribution, you can't measure it, but it's converting shrinkage strain to an equivalent temperature distribution so that we know what to do with it, because we know very well how to handle temperature distributions. So in ASH2ME, we saw that these were the levels of sophistication. So the transient nonlinear temperature distributions, the shrinkage strain as well as the built-in curling is what ASTO-ME PVG considered in its analysis, and we saw how it can be considered. Now, in today's lecture, I want to explain to you how IRC 58 does this sort of consideration, whether these are considered, and if they're considered, how are they considered. So, the lecture objectives today, after that introduction, is I'm going to explain how climate is characterized in IRC 58 2015. Again, climate, we'd already talked about what are the variables of climate. For example, you have air temperature, you might have wind speed, you might have solar radiation. So, these are climate variables. We talked about how they're characterized using the EICM in ASTO-ME PVG. We'll see how they're characterized using IRC 58. I will also, okay, we will not actually be doing different type of traffic loads, so this one should be out. So, traffic loads we'll talk about later when we get to an example. And so, today we'll basically be sticking on looking at climate characterization. So, these two we're not going to look into today. Okay, so let's just have a brief recollection. As I just mentioned, what are the effects of climate when we consider a JPCP section? Basically, we have three effects which are important from a mechanistic perspective. There is a fourth effect, which is creep, but we're not going to talk about that. But there are largely three effects. One effect is curling. Now, curling happens due to transient temperature distribution, that depending on the position of the sun, depending on the wind, depending on the air temperature, etc., you have a temperature distribution inside the JPCP. So, if this is the JPCP, just the surface layer, you do, and you have some sort of reference temperature T naught, you do have some temperature distribution which develops, and that temperature distribution keeps changing over time. That's what we call a transient temperature distribution. Now, as we talked about that due to transient temperature distribution, we get two types of stresses. One I've already written down in the slide, which is curling stresses. Curling stresses basically happen when we have this non-linear component, and when we have this non-linear distribution, and a linear component of that distribution causes the pavement to try to assume a certain shape. The shape could be like this, so you could have curling upwards, or the shape could be like this, that is, you could have curling downwards. So, depending on whether you have curling upwards or curling downwards, the pavement tends to take that shape. This is very important. It tends to take the shape, it doesn't actually take it. What happens is it tends to be restrained. It tends to be restrained by an external load as well as by self-weight. So, because of that additional restraint which is coming, a stress develops. Remember, stresses develop wherever there is a restraint to strain. So, because there is a restraint to the strain, the stress is going to develop, and those stresses are then called curling stresses. Because the curling stresses are based on transient temperature distributions, the curling stresses too are transient. I invite you to go back to a particular lecture on thermal linearization which we performed, and in thermal linearization, we saw that how we can take the time part of this temperature distribution. So, it's not just that the temperature distribution occurred, but when does it occur and how do you relate that to traffic? We looked at that in that lecture on thermal linearization. So, you might want to go back and just review that. In addition to curling, I had also pointed out that there are two more effects. One, you can have a expansion or contraction of the slab. That is, you have a uniform temperature distribution component. Now, the uniform temperature distribution component I had mentioned back then is basically a certain component which we ignore. Why? Because at most there's a little bit of base friction that's preventing that sort of movement. That's a relatively negligible amount. It's not particularly important. And so, relative to curling stresses, it's negligible. So, we generally ignore it. But there is a third component which we do not ignore. And that third component I have mentioned was the eigenstresses. So, the eigenstresses basically occur because this non-linear temperature distribution will try to warp the cross section of the slab in such a way that a section which was plane before this temperature distribution will try to be not plane. So, it will try to take a non-planar shape after the distribution is applied. But these slabs are usually analyzed using the medium thick plate theory or the Kirchhoff-Love plate theory. One of the main assumptions in Kirchhoff-Love plate theory is that transverse shears are not admitted in the solution, and this theory has been fairly well validated to explain the behavior of rigid pavements quite well. So, if transverse shear is not allowed, transverse strains is not allowed, what that means is we cannot have a cross section which is no longer plane after bending. In that case, this non-linear temperature distribution is trying to assume a non-planar shape for the cross section, but because because transverse shear is not admitted, an additional stress is required, and additional stress will be generated, which will prevent this cross section from assuming a non-planar shape. So, the planar shape before bending is going to remain plane after bending, and in order to enforce that, these additional eigenstresses have to be accounted for. So when we talk about the transient temperature distributions, we are looking at curling. We are also looking at eigenstresses. That's one effect of climate. Another effect of climate comes in from shrinkage. This is of course built on moisture. So the idea is at the very top of the pavement on a very small depth, typically somewhat like 50 millimeters in depth, you have a very sharp distribution of the humidity. So if I look at relative humidity, you have the ambient relative humidity RH naught. You're going to have the same value at the surface. Below the surface, the relative humidity is going to change very rapidly until basically becomes RH of 100%, which is its saturated certain depth into the concrete. Because of this very sharp distribution of the relative humidity, you have hygroscopic stresses, that is stresses which are formed due to these moisture gradients. These hygroscopic stresses in that case are going to generate a certain amount of strain. That strain is what we call shrinkage strain. We usually model it by converting the shrinkage strain into an equivalent temperature strain, TSH. And in that TSH, we handle just as we would handle curling. Of course, this is not transient. It is transient initially. We are generally concerned about this only in the first couple of days after curing, when the concrete is still relatively weak. After the concrete has gained sufficient strength, then this is not much of an issue. But the problem with shrinkage strains is if you don't account for them properly in the design, they can lead to very premature cracking of the pavement, and that generally can be a very big problem. You will have a lot of cracking before even the first car or first truck has gone on the pavement. So naturally, that's a major problem if such a thing is not accounted for. The third and last climate effect that we consider is built-in curling, and in India we sometimes also call this zero stress temperature difference. So what happens is that initially when the concrete is laid, it's still in plastic condition. Now when it's in plastic condition and it is laid outside, so it is outdoors, is exposed to the environment, and therefore even this concrete with a plastic condition is going to have some type of nonlinear temperature distribution inside of it. For the same physics that leads to the generation of nonlinear temperature distribution in elastic slabs, the plastic concrete will also have such temperature distribution developing in it. But because it's plastic, this nonlinear temperature distribution is not going to generate any additional stresses. So what happens is initially, when the concrete is still in plastic condition, when it has not yet set, it has assumed a certain temperature distribution with a zero stress. Now, when the concrete finally sets, when it finally hardens, it is going to harden in such a way that it's going to have this temperature distribution built inside of it, hence the name built-in curling. It's going to have a temperature distribution built into it which corresponds to the zero stress condition, hence the name zero stress temperature difference. Therefore, when we are actually trying to model these stresses in the pavement under a transient temperature distribution after it has hardened, of course also with some loading, when we try to model curling, in other words, we have to take into account that our zero stress condition is not a flat slab condition, that is a slab which has a constant temperature, reference temperature. The zero stress condition actually includes a certain amount of temperature distribution which was built in during the time when the concrete was setting. That phenomenon we call built-in curling. And we saw that in the AASHTO MEPDG, this built-in curling was used rather simplistically. It was just generally accounted to be minus 5.6 degrees Celsius. Now, there is a lot of literature which explains different sort of interesting ways to take into account. Indeed, a newer program called Pit Slab, which I have also been part of, there we have tried to incorporate some quasi-static calculations of these temperature distributions at early age. So it's a relatively complicated and active area of research to properly characterize built-in curling. AASHTO MEPDG does it in a relatively simplistic way. And in today's lecture and in the subsequent lectures, we will see how IRC 58 takes this into consideration. So in short, to summarize, there are three major effects that we are considered with when we are talking about climate effects on JPCB. That is curling, shrinkage, and built-in curling or zero stress temperature difference. Okay, just as a reminder, I already mentioned this, and this is a slide which you have seen previously also. So the transient temperature distribution is almost always non-linear in nature. So I had given you a couple of images over here to show you that the temperature distributions are non-linear. I had asked you to figure out which of these temperature distributions correspond to the morning and correspond to the night, or during the day and during the night. And I hope you've taken some time to try to figure that out. Just as a hint, during the day, you'll have a higher temperature at the top and a relatively lower temperature at the bottom. And during the night, it will be the opposite. So when you look at these figures, that should help you figure out which one is during the day and which one is during the night. And as I just discussed, this non-linear temperature distribution, so what AASHTO MEPDG does is the EICM actually calculates this non-linear temperature distribution. And then this can be decomposed, and we saw the formulation for doing that. This can be decomposed into a constant, into a linear component, as well as some sort of a non-linear component. The constant component we generally ignore because base friction is generally quite negligible. The stress is caused due to base friction. This linear component leads us to curling, but only if we have an external load associated with it. On its own, the linear component does not generate any stresses. And then we also saw for the non-linear component, this is what generates the eigenstresses. These are generated without any external load. Hence, it's called an eigenstress. It's a characteristic stress which is characteristic to the pavement itself. It's not dependent on any external load. So this we saw previously, and we saw that the AASHTO MEPDG actually does all of these calculations and includes both curling stresses and eigenstresses in the total critical stresses which are developed in the pavement. It does that, as I mentioned, as follows. The EICM actually calculates the hourly pavement temperature profile for each location. This is actually one of the slowest parts. This is relatively slow. This is actually one of the slowest parts of the calculation to do this extensive calculation. Remember, it's an hourly calculation for 20 to maybe 40 years, even 50 years if you're using CRCP. So it's for 20 to 40 years worth of hours. So you can calculate how many hours it has to do this calculation for. While each calculation itself is relatively fast, it takes a couple of milliseconds per calculation, the sheer number of calculations that has to be done can make this a somewhat slow process. And you need a lot of simplification which has been done in subsequent models. We talked about simplified variations of the MEPDG. A lot of simplifications which are done in subsequent models is to try to find easier ways to do this characterization without having to analyze hourly data for 20 to 40 years. One of those simplified ways is actually used in IRC 58, and we'll talk about it a little bit later in today's lecture. Then we just talked about this decomposition of the transient temperature components into its constituent components. So that's the constant component, the linear component, and the non-linear component. So I won't repeat what we talked about. Addition of a built-in curling, which is minus 5.6 degrees Celsius temperature difference. So the idea is delta T for built-in curling, we add a delta TL is equal to minus 5.6 degrees Celsius into the analysis in the AASHTO MEPDG. We'll see what we do in IRC 58 shortly. And then there is fictitious shrinkage temperature. I already mentioned this, so I won't repeat it again. Okay, one last thing I want you to remember before we go full on into IRC 58. This map I had shown you previously, but I thought it's a good reminder to show you. So what this map is, this is taken from this journal on climate change. It is the average annual air temperature over India. And what we see here is, you would think the average annual air temperature is more or less a function of latitude. The closer you are to the equator, the hotter it is. But it's actually more complicated than that. The average annual air temperature is also a function of, for example, climate. If it's a relatively dry climate, you can have a higher air temperature. If it's a relatively moist climate, which gets a lot of rains, gets a lot of clouds, gets a lot of wind, sea breeze, land breeze, etc., then you can have a relatively cooler climate, regardless of where the latitude is. Furthermore, climate is also the average air temperature or the climate behavior of air temperature that is also affected by generally how much cloud cover do you get. Some locations get a lot of cloud cover just because they're more humid, they might be near a water body. Some get less cloud cover just geographically, they're in a place that doesn't get a lot of moisture, that doesn't get a lot of disturbances that bring in clouds. And in India, then we also, maybe perhaps you've heard, we get something called western disturbances which come in from Pakistan, and they generally tend to alter the weather as well at fairly regular intervals. So it's for that reason in this map, you'll see that there is somewhat, if you see very closely, there is somewhat of a relationship between latitude. So as latitude is increasing, to an extent, you can see that the temperature does seem to decrease. So to a weak correlation, it is there that the higher latitude you have, the lower the air temperature you have. Particularly if you go up in the mountains, then certainly we tend to do have lower air temperature. But you can see that it's not perfect correlation. So for example, around here in Ahmedabad, Gandhinagar, which is where I am, here you tend to have a very hot temperature, and surprisingly a similarly hot temperature can be seen on the southeastern coast of India, that is in Tamil Nadu as well as in Andhra. So it's not a very straightforward analysis to know where do you have the highest air temperature and where do you have the lowest air temperature. The reason I showed you this, I'll come back to you. I just wanted to emphasize in this that in India, you tend to have a variety of different zones of, if you're just looking at air temperature, you tend to have a variety of different zones. So here you might have a zone, this part over here might be a zone, the Western Ghats might be a certain zone, the mountains might be a certain zone. So we tend to have certain climatic zones. They are not completely related to latitude. They do have a weak correlation with latitude, but it depends on a variety of other factors as well. So just keep that in mind, because that becomes very important as we go into understanding IRC 58. Okay, so what are the climatic effects which are considered in IRC 58? I already mentioned there are basically three climatic effects as such that should be considered. That is curling due to transient temperature distributions, shrinkage, as well as built-in curling or zero stress temperature difference. Now, IRC 58 straight away actually is quite silent on shrinkage. It does not have an explicit consideration of shrinkage. So that's why I've marked this out, I've cut this out in red beforehand. There is no explicit consideration of shrinkage in IRC 58. Also, for curling, what I've marked out over here is due to transient temperature distribution. So, as I said, in the MEPDG, you have the EICM program. The EICM calculates the hourly temperature distribution throughout the entire service life. So, the temperature distribution and this decomposition of temperature distribution, it is changing actively. Then, of course, there is the thermal linearization process where a certain range of values is chosen statistically and combined with traffic. Please go back to that lecture. But fundamentally, you do have consideration for the fact that at least on a monthly scale, if not an hourly scale, the temperature is changing. And the EICM and the MEPDG acknowledges that and takes it account into its calculations. Now, IRC 58 also acknowledges that. So, IRC 58 does acknowledge that there is a change in temperature and ideally hourly temperature calculation should be done. However, its recommendations, so the recommendations are based on one level, in the sense if you don't have any more information, then you should use the recommendations of IRC 58. It does encourage to use other variations of it, which we'll talk about later today. But if you just follow the recommendations of IRC 58 as is, without supplementing it with additional data, then there is no transient consideration of the temperature. So, it first of all considers only curling, that is this delta TL component. It considers this delta TL component, and we'll see how it considers in a moment, but it considers this and it assumes that this is going to be constant for a particular location. We'll talk about locations in a second. It assumes that this value is constant for a particular location throughout the service life. So, there is no consideration of the fact that this delta TL is going to be changing every hour of the analysis, or at least in every month you might have a different value that could be used. That consideration is not there as of now. And so, in the current version, curling is considered, but there is no transient behavior as such within the curling. Built-in curling or zero stress temperature difference is also considered. We'll see in a second how it's considered. As such, we add minus 5 degrees Celsius. So, in AASHTO, the value they use is minus 5.6 degrees Celsius. In IRC 58, the value recommended is minus 5 degrees Celsius. Now, this is for the entire country. That's not unique. Even MEPDG, just for the entire United States, basically has one value to use. But just keep in mind, this delta TL is for different locations. Certain values are recommended. We'll see those values in a second. But for built-in curling, the same value of minus 5 is recommended throughout the entire country. Okay, so let's see a little bit about what AASHTO says about consideration of what IRC 58 says about consideration of temperature. So it says, now this is a statement of physics, temperature differential between the top and bottom fibers of concrete pavements causes the concrete slab to curl, giving rise to stresses. The reason I highlighted this is almost correct. There is indeed a temperature difference between the top and the bottom fiber causes the slab to tend to curl. So, my only sort of grouse with this, it says it causes the slab to curl, it causes the slab to tend to curl, and it is under the presence of external loading then that curling actually generates stresses. So if you have that temperature difference and there is no external loading, there are actually no stresses which are developed. So, that's just a little bit of a correction which I'm making to this. Okay. As far as possible, so it first of all says that there is a temperature differential. So, the effect of climate is considered through the effect of a temperature differential, again which I said delta TL. Note, this is the linear temperature differential. We'll talk a little bit in terms of how the non-linear component is considered over here. As far as possible, temperature differential values estimated realistically for the given site using relevant geographical parameters and material characteristics should be used for analysis. This is basically saying EICM. So, what the recommendation is, to the extent possible, you must consider geographical conditions, you must consider material characteristics, which could be thermophysical characteristics, which we talked about in an earlier lecture. That could be albedo, thermal conductivity, heat capacity, diffusivity, and emissivity. So, please go back to those earlier lectures if you just want a revision on what these different terms are. But what IRC 58 says is, as far as possible, these considerations of various types of thermophysical material properties, geographical parameters, climate parameters, they should be taken into account in performing the analysis. Unfortunately, in practice, mostly these are never taken into account. It's not, I would say it's not particularly difficult. And in today's lecture, I'll show you some results from some research I've been doing. So again, I've tried to put in a little bit of research topics into this lecture. So you see a flavor of what new work is happening as well. But I will show you a little bit of research in terms of how these can be calculated and how these properties can be considered. In practice, however, at least to the extent I've seen, it's never actually considered. Instead, what IRC 58, what it says is, in the absence of any local data, the maximum temperature differential values given in table 1 may be adopted for pavement design. The maximum values given in table 1. I'll show you table 1 in a moment. But as you see over here, it says that you should use the philosophy of the EICM, if not outright the whole program. The philosophy of the EICM should be used to consider temperature distributions. If that is not available, which is most of the time, then certain values are given in table 1, which I'll show in a second. They may be adopted instead. Now, one last thing I want to highlight before I show you table 1. The variation of temperature with depth is non-linear during the day and nearly linear during the night hours. Now, that's an observational comment that they've basically put some thermocouples in various sections and measure it. They do recognize that there is a non-linear temperature distribution. They say that during the day, it's definitely non-linear. During the night, it is nearly linear. This statement is generally correct. So based on my experience with research as well, this statement is generally correct, that during the day when you have the sun, basically, you have a fairly non-linear temperature distribution. Just the presence of the sun and sunlight can really drive a lot of temperature distributions. During the night, it is correct that because you don't have the sun, the entire pavement is more or less trying to reach equilibrium. So you tend to get a somewhat linear, nearly linear temperature distribution. But what is key, which I think the IRC code does not fully acknowledge, is during the most critical hours, which is during sunset and sunrise. So during sunset and sunrise, you actually have the most dramatic change in the boundary conditions. Namely, either the sun is gone, that means suddenly you've removed a very large part of the boundary condition, or the sun has just started shining, that means a very large amount of energy is actually suddenly coming, and that's a dramatic change in the boundary condition. During sunset and sunrise, during these particular critical hours, you can actually have some very dramatically non-linear temperature distributions. So that is something which is not fully acknowledged, I think, in the code itself. Anyway, but that's how the code tends to look at temperature distributions. Certainly non-linear during the day, somewhat linear or almost linear during the night. Okay, now going back to what we were talking about, table 1. So here is table 1, which is from IRC 58. Table 1 is recommended maximum temperature differences for concrete slabs. So as I showed you over here, first of all, the first statement that the code makes is that you should try to consider your own local climate data. In practice, however, that's not really done. So what it says is, in the absence of local data, maximum temperature differential values, so these are meant to be very conservative values, they are provided in table 1. So table 1 does it as follows. So basically, it divides the whole country into 7 climate zones. Now, if you think and pause a little bit, you think that 7 is actually a relatively small number. Given, the sort of continental sized country that we have, 7 is kind of a small number to do these zones in. Nonetheless, that is what is recommended. As I explained previously, these zones are not going to be completely based on latitude either. There is going to be consideration for local topography and local climate as well. So these zones somewhat don't correspond to exact geographical locations. Widely interspersed geographies are also put into the same zone. So for example, what I particularly want to talk about is zone 1 is actually all hilly regions. So hilly regions of Uttarakhand, West Bengal would be Cooch Behar and the parts near Sikkim, Jammu and Kashmir, Himachal Pradesh, Arunachal Pradesh. So Jammu and Kashmir here referring to Ladakh in those parts. So those upper reaches, the high Himalayas, that is fully put into one zone called zone 1. You can see there's quite a lot of variation. So from Arunachal in the east to West Bengal and Uttarakhand in the middle, all the way to Ladakh, all of that, and they're at very different latitudes. If you recall the map, they're quite at different latitudes. They are grouped into one zone, which is zone 1. Another zone which you might look at, for example, is zone 3. And particularly, I mentioned zone 3 because we're going to come back to an example of this. In zone 3, you have Bihar, Jharkhand, West Bengal, Assam, and eastern Orissa. So that's sort of the eastern parts, but excluding hilly and coastal areas. So coastal areas are given somewhat of a different condition. They are mainly in zone 6 and zone 7. So zone 6 is for coastal areas bounded by hills. Zone 7 is for coastal areas unbounded by hills. And similarly, you have these other zones which you can look at. Now, for each of these zones, a recommended value of maximum temperature differential. Again, this is meant to be delta TL for design. So, it's meant to be a conservative value. So, a recommended value is provided depending on the thickness of the JPCP slab. And the slab thickness could be, so it's for 150 mm, which is actually quite a thin slab, 200 mm, 250 mm, and 300 to 400 mm. Generally, you could go above 400 mm, but the change in this is very small. So, generally, even if you're above 400 mm, you'll just stick to the value at 400 mm. So, you're given these values. Now, if you have any value in between, for example, if you have 280 mm, you could do an interpolation, or you could just do a nearest neighbor kind of thing. So, for example, if you're at 290 mm, well, the nearest value to that is 300, so you might just pick up the value of 300. So, sometimes you can do linear interpolation, sometimes you can do a nearest neighbor value just so that you stay on the conservative side. And what you see for each of them, a different value of delta TL is recommended. Now, if I pick up just one column, let's see a 200 mm thick column, which is a reasonable amount of thickness for somewhat reasonable amount of traffic. What we see is in the hilly regions, the temperature difference recommended is 13.1. As we go further south into the country, that temperature difference increases. You can get 16.4 for Maharashtra, Karnataka, Andhra, Western Odisha, and Northern Tamil Nadu, excluding hilly areas. It can actually be 19. That's a very high temperature difference value to use. And in coastal areas, if there are hills, the value is a little lower, 15.8. If there are no hills, the value is around 17. Furthermore, as delta T increases, so if we consider just zone 3, for example, as the thickness increases, as you see, the value of the temperature differential recommended also increases. So, at 150 mm for zone 3, it recommends using 15.6 degree for delta TL. And as you further increase the thickness, it goes to from 15.6 to 16.4 to 16.6 to 16.8. So, the value tends to increase. Now, one question which is, it's a good question to ask, but I don't think is asked enough, is where is this data coming from? This data, and the answer is actually inside the code itself. There is a little footnote which is provided at the bottom of the code. Let me read it out to you, and it might surprise you, but let's see. So, the above temperature data was recommended by the Central Road Research Institute, New Delhi in 1974. I will take a hazardous guess that all of you were born after 1974. So, this data is older than all of you. The data for hilly regions of Jammu and Kashmir, and including Ladakh, Himachal Pradesh, West Bengal, Uttarakhand, and Arunachal Pradesh are suggested in zone 1 in the absence of available records. So, let me make some comments. I'll go back to the slide I just skipped, but let me just make some comments on this. So, IRC 58 2018 divides the entire country into just 7 climatic zones. By the way, although I write 2015, if you actually go back to the earlier edition, so if you go back to the 3rd revision or the 2nd revision, it's almost more or less the same. These recommendations really have not changed all that much since probably the very first version of IRC 58 which came out. So, this is sort of something which has persisted, at least in my opinion, a little bit too long, and it is time to actually try to update these values. Okay, so IRC 58 2015 divides the entire country into just 7 climatic zones and suggests delta T to use for design purposes for each zone. Now, again, I should add here, if you read the code exactly, which I read out to you a couple of slides ago, the recommendation is to try to use local data. But in practice, nobody actually uses local data, and we'll see a little bit some of the research which my research group is doing, where we have tried to do something of that sort. So, nobody's actually trying to use local data. So, these values mostly are used uniformly across the country in JPCP design. The data itself is from 1974. So, you'll agree with me, it's very old data. It's really time to do some updates to this data. It's based on a limited number of sections. Now, I haven't been able to source the original document itself. I mean, 1974, nothing was digitized, so it's difficult to actually find the original documents. But it was based on a very small number of sections. It was not possible to do very extensive data collection back then. And after that, there hasn't been really much of an update. There's been a little bit on the flexible payment side. On the rigid payment side, there hasn't been a lot of updates since 1974. So, it's based on limited sections which have been not updated. Zone 1, as I pointed out, which is the upper Himalayan regions, they are more of a guesstimate. So, basically, there was absolutely no data over there. There's a little bit of guesstimate, which basically means a couple of people sit together and try to judge, looking at the existing data outside those areas, try to judge what would be a good piece of data if you went significantly higher in elevation. But they are more or less guesstimates. One important thing is the entire discussion over here is based on this delta TL value, right? I already told you this delta TL is basically the curling stress component. So, delta TL, that temperature distribution along that temperature difference, linear temperature difference, along with some external loading, together they're going to cause curling stresses. there is no explicit discussion of eigenstresses. So there's no recommendation on what to do about the fact that you are characterizing a nonlinear temperature distribution. The code acknowledges we have a nonlinear temperature distribution. There is no guidance on the fact that if you have a nonlinear temperature distribution, how do you consider it? It only tells you what is the equivalent linear temperature component you should use, but not what to do about the nonlinear part of it. You can definitely have two nonlinear temperature distributions that give you the same linear component, but different nonlinear components. And so there's no explicit explanation of what exactly needs to be done, at least on the side of the temperature. It does recognize, however, there is a nonlinearity. So we will see more about this particular issue a little bit later. So local data is recommended, but it is generally never used. Now, one thing, just this slide I skipped, I wanted to finish this. These delta T values which are recommended, these are for bottom-up current. So that is when delta TL is greater than 0, these are the values to be recommended. If, however, you have top-down cracking, that is delta TL is less than 0, the recommendations are that you should use the same values in this table divided by 2. Do not multiply by -1. This is, we'll go back in our next lecture when we look at critical stress analysis in IRC 58. This thing will come back. Do not multiply by -1. For example, let's open this. So for example, let's say we're looking at Bihar, zone 3. This is actually an example I'm going to use soon. So that's why I'm taking this example. Let's say we have 200 mm thickness and so we have 16.4 degrees Celsius. So for bottom up cracking, you should use 16.4 degrees Celsius. For top-down cracking, the recommendation is use 16.4 divided by 2 and that works out to 8.2. Of course, there is also the issue of built-in curling. I'll talk about that later. But it recommends that you use 8.2. Do not put the minus sign in front of it. And technically, it is minus 8.2. That's how you know it's top-down cracking because it's a negative value. But the recommendation in the calculations is don't put that minus sign over there. Consider delta TL then to be some sort of an absolute value. Okay. So I had given you a hint and let me now share that with you. So the main issue which I discussed is, so that basically concludes, if you look at IRC 58, how it considers temperature distribution. And then this critique which I've put over here, that the data is relatively old. There is a recommendation to use local data. In practice, is essentially never used. But there is a need for it because this data is, well, it's almost, we're getting to the point where it's around 50 years old. So there is a need to update this data. How would we update the data? That's actually been some research which has come out of my research group. So my student, Mr. Avinash Kumar Jha, who was an MTech student at IIT GANDHINAGAR, he actually tackled this very problem in his thesis. So I thought, again, my philosophy in this class was to mostly stick to whatever has been done to give you a more textbook-like explanation. But wherever possible, I wanted to give you a flavor of a little bit of research. I've done that previously in the ASHTO MEPDG. I thought it would be a good idea to also give you a little bit of research flavor on IRC 58, just to maybe some of you will be interested to continue and focus on research in these areas. So what my research group did is we did research on updating these values. So these delta T values, updating these values using computational methods. Now, why did we use computational methods? It's basically the same idea as the EICM. Why don't we use field data all the time? Why should we even resort to computational methods? The challenge with using field data is it's very difficult to collect the field data. Right? India is a very large country. We have a variety of different type of climate conditions. We have a variety of different type of road conditions. Our climate in particular, because we have a monsoon season and then it's much drier outside, we can have very dramatic changes in temperature just in a short period of time. So because we are such a large country, collecting a vast amount of field data is actually very difficult in practice. It's quite difficult to go around collecting a large amount of field data. That said, we have actually made a lot of success in India in collecting meteorological data. So IMD, the Indian Meteorological Department, they actually have hundreds of weather stations, which are called automated weather stations, AWS. So they actually have a network of hundreds of AWS sensors distributed all over the country. They are not measuring pavement temperature. They are measuring air temperature, wind speed, solar radiation. The things that pavement temperature depend on, those are being measured. So in comparison, there is not a very extensive network of thermocouples to measure the temperature distributions throughout the country. In the US, they do have the LTPP program, where they do measure it for a fairly large network. We don't have such an equivalent program in India. So in this particular study, first of all, we understood that there is not a lot of field data. And if you try to collect a large amount of field data, it's years of effort. Again, we're looking at climatic effects. So you should not be collecting 1 year of data. 1 year, you can have an exceptionally hot year, exceptionally cold year. You should not be collecting 1 year of data. Climate generally is defined as 30 years. So you actually need to do 30 years worth of data collection, and as of now, we simply don't have that sort of data in India. So that's why in this paper, what we did was we do from our AWS stations, we do have, if it's not 30 years, we have a couple of decades worth of data for air temperature or the climatic condition, the atmospheric conditions. And then what we did is we used computational methods very similar to the EICM, not exactly the EICM, but very similar to it. We used methods which are from is very similar to the EICM to calculate the temperature distributions, take into account the atmospheric conditions which we get from IMD's AWS sensors. So we chose this to answer the question on the slide. Why did we not use field data all the time? Because it's very difficult to collect data. First of all, in terms of space, the number of thermocouple sensors you need, the amount of data acquisition equipment you need, it's quite prohibitive in terms of expense, in terms of maintenance. It's difficult to collect this data. And secondly, it's also in time, because you don't just need the data for 1 year, you need the data typically for 30 years in order to make any design sort of recommendations. Very difficult to collect that sort of data for pavements in India. Instead, what we do, but we do have a lot of data for atmospheric conditions using these IMD's AWS sensors. So what we did is we used computational methods because we took the best data we have, which is IMD's AWS sensors, and then we used a fairly sophisticated numerical model, very similar to the EICM, and then we calculated the pavement temperature distribution out of that, of course taking care for validation, etc. So here is a little bit of what we did. We decided to start by just checking out these zones. So by the way, the title of the student's thesis was Improved Estimates of Temperature Distribution for Design of JPCB Pavements in India and Nepal. So student was from Nepal, so he also wanted to include Nepal. Of course, this course is based on American and the Indian standards, but you should just know the Nepali standard also references IRC 58. So Nepal, they tend to follow the IRC 58 standards. They just put slightly updated recommendations for temperature distributions instead. So what this particular student did is we actually took India and Nepal, the two countries, and in India we took the 7 climate zones as IRC 58 defines, and then we also chose an additional zone number 8, which was for Nepal. Within each zone, then we selected 3 major cities for which we could collect the relevant data. So we selected these 3 major cities in each of these zones, and on this map you can see what the cities are. So you can see we have a fairly large distribution of the cities covering all the zones, at least the zones as defined by IRC 58. I'm not saying these zones are necessarily correct, and there could be, realistically, there should be many more zones, but this was a starting point. So in total, we had 8 into 3, we had 24 different locations that we considered. Now, we had a question of where do we get the climate data, that is the atmospheric data, where do we get the data from? As I mentioned, IMD does have AWS data, and that's basically observational data. What we found is a lot of this data was going back around 20 years, so that was not quite 30 years. We were hoping to get 30 years because that's what climate means. We could not actually get 30 years. There was a fair amount of issues with data cleaning, etc. So instead, we had the other choice to use reanalysis data. I've pointed this out before in one of the earlier lectures on MEPDG. Reanalysis data is sort of numerical data, but it has been validated very, very carefully, and from a scientific perspective, it's very solid data. It can be used pretty well for design purposes. In fact, MEPDG also uses reanalysis data. So an earlier version of AASHTO Pavement ME or MEPDG, it also used to use observational data, and there was limited amount of data. Now the modern MEPDG also uses reanalysis data. I'll talk about that in the next slide a little bit more. But what we chose to go in the same route for our particular research, that is, we decided to also use reanalysis data. In the figure here, what we have is this ASOS is basically this AWS observational data. We had the distribution of the observational data. We tried to do certain amounts of interpolations. We weren't actually very successful with interpolation, didn't work out too well. And then reanalysis data, what we see is in the reanalysis data, the major part of the data. So here, this was just looking at air temperature. We also looked at other variables. On average, the average of the observational data and the average of the reanalysis data was pretty similar. It's the outliers which were different. The observational data had more outliers and the reanalysis data had fewer outliers. That's typical. That's generally how these numerical models for observations work. They're good for design in the sense they're good for taking the average behavior. Extreme values tend to be not considered in this. But anyway, we decided to go for reanalysis data. That's also, by the way, what is used in the MEPDG. So this slide in that one, I had rushed through it, so I thought let me just repeat this once. So MERA 2, which is the modern era retrospective reanalysis for applications. This is a product actually from NASA, believe it or not. They actually develop a reanalysis product. So it basically tells you at certain points, going back something to last 30 or even 60 years probably. I need to check this, could be anywhere from 30 to 60 years. They've calculated numerically and validated very well what is the hourly temperature distribution and hourly climatic conditions at a variety of locations across the world. So it's a very, very good database that can be used to get high quality, cleaned data, which the only issue with it is it doesn't really match the outliers very well. So outliers or the extreme values will not be taken into account, but the main part with the bulk of the mean behavior of the atmospheric conditions, that is taken into account pretty well. By the way, the data can actually be freely downloaded. So this particular from FHWA info page, if you go to this link, you can actually download this particular data set for free. So MERA 2 data set is freely available. We actually use a slightly different data set for our work. We use what is called the ERA 5 data set, European reanalysis data set. So we used a slightly different one, but it's also pretty well used and validated one. Now, you can of course read the literature if you want all the details. I'll just show you some of the results which came out. So what we're looking for is what are the temperature differences for top-down cracking for the entire period of analysis. So here again, we're looking at those cases where delta TL is less than 0. Now for each of these cities, we were looking at a particular zone. I think this was zone 7, if I'm right. But for each of these zones, we basically took each of those 3 cities and then we plotted, and of course for each, these are actually the individual zones. So from zone 1 to zone 8, we took 3 of those cities and we did the analysis, and this is for a 150 mm thick pavement, and then we calculated what is the delta TL value when it's less than 0. This is the distribution. So this is called a box plot. This middle part is the main part of the data. So this gives us the 25th, the 50th and the 75th percentile. And then we have the outliers or the extreme values on either side. Of course, everything is less than 0 because by definition, top-down cracking occurs when delta TL is less than 0. So what we see over here and what we pointed out over here, this vertical line, this dotted lines over here, these are the values which are recommended by IRC 58. So what we saw here is the IRC 58 values clearly, it's not that they are completely out of this range. It's not that the values are somewhere over here. They are within the range of our observations, but they tend to be on the higher side. They tend to be somewhere along the 90th percentile or 95th percentile or so. So the recommended values are on the much higher and the more conservative side. If you looked at the bulk of our data, if you looked at the mean or even the median or even the 75th percentile, it tends to be much lower. So what we get from this data is the values recommended in IRC 58 are actually very conservative, not somewhat conservative, they're actually very conservative. I'll show you a summary to further highlight this point. So they tend to be very, very conservative values. And indeed, the code actually acknowledges that briefly because they do say that if you go back to an earlier slide which I showed, these values which are recommended are actually the maximum design values. Maximum kind of hints that these are meant to be conservative values which are used. Okay, so what we did is we took this temperature distribution which we had. So again, for about 30 years, we had hourly temperature distributions, and then for each hour, we calculated delta TL, and then we compiled all that data together. So it was thousands upon thousands of lines of data for every single city, that's 24 different stations, and for every single pavement thickness that was considered. And then what we did is we took the 90th percentile value. So we thought in this distribution, again following the IRC philosophy, if we had to use a single value for design, we should probably use a relatively high value to be conservative. So we picked up the 90th percentile value. And what you see over here, if I just pick on zone 2 for a second, the IRC 58 recommended value, if you look at zone 2 for bottom-up cracking, the recommended value is 12.5, and we see the values we got for zone 2 are relatively in the same range for 150 mm. So it's 12.5, 12.0, 12.1, relatively close to 12.5. But if you look at top down, then what we see is that the recommended value is minus 6.2. But the value we got was actually minus 1.8 roughly for each of the locations. That's very different. So minus 6.2 is very different from minus 1.8. So what we see is we actually had significant variations in temperature distribution. At least for top-down cracking, we saw significant deviations in the value recommended in IRC 58 versus the value we calculated. For bottom-up, although in this example they were relatively close, there are other places. For example, if you look at zone 3, recommended value was 15.8, 15.6, but the values we got were around 11.9 and 10.2 and 11.8. So we did see that there are notable differences. And in all cases, we found the values recommended by IRC 58 tends to be on the higher side, so it tends to be more conservative. So that's sort of a little understanding of what that statement said, that the maximum values to be used, they are on the conservative side, and in this research we did so that they tend to be conservative. You need not use such high values. Similarly, for zone 5 to zone 8, you can look at the research yourself. We got similar results in all cases. Now, one other interesting observation that IRC 58 makes is as follows. What they say is it is ideal to carry out hourly CFD and cumulative fatigue damage analysis, but data for carrying such an exercise is not available. So they do recommend that hourly analysis should be done similar to MEPDG, but they acknowledge that it's very difficult to get such amount of data. It is suggested that the maximum positive and negative temperature differentials may be assumed to be constant for the 6-hour period from 10 a.m. to 4 p.m. This is for bottom-up cracking, and then 0 a.m. means midnight to 6 a.m. for top-down cracking. So they actually recommend do the analysis don't do it for 24 hours, do it for 6 hours during the day, 10 a.m. to 4 p.m. and 6 hours during the night, that's midnight to 6 a.m. The slab may be assumed to be free of curling stresses for the remaining 12 hours for the purpose of fatigue damage analysis as well as fatigue damage caused by the combined action of load and temperature differential. This timings refers to Indian Standard Time and may be different for different geographical locations. So it's very interesting. They recommend you do an hourly analysis, but they do acknowledge that it's difficult to get that sort of data. So instead, they recommend just combine the day analysis for 6 hours during the day and 6 hours during the night. It's a very interesting observation. I will say from the research that we perform, we don't agree with this observation. We think it's necessary. And the reason is that this sunrise and sunset, which I talked about, you can get very significant changes of temperature differentials during sunrise and sunset. And you see clearly these timings do not include sunrise and sunset. So I, at least based on the research our group has done so far, I don't really think this recommendation is actually warranted. Anyway, the most important thing to note is damage calculation is not incremental. It recommends an hourly incremental fatigue damage, doesn't actually use it in practice. Okay, the other thing about built-in curling, yeah, let's just keep going. So the other thing about built-in curling is that I already mentioned the built-in curling value recommended is 5 degrees Celsius. The recommendation, so that's what's pointed out here, use 5 degrees Celsius for built-in curling, but it provides another interesting recommendation. If the maximum positive differential, so for example, if you're looking at bottom-up curling, if suppose the temperature difference is 20 degrees Celsius and the built-in curling is always a negative value, so then you're supposed to subtract 5 from this. What the code says is don't do this subtraction, stay on the conservative side. 5 degrees Celsius reduction is generally not made for the design of bottom-up so that it's somewhat conservative. But if suppose for our top-down curling, the temperature difference is minus 10 degrees Celsius, then it says you include this 5 degrees Celsius and use a total of 15 degrees Celsius. Again, the minus sign is generally not shown. We generally use the absolute value in calculations. But the idea is for bottom-up curling, don't consider built-in curling. For top-down curling, consider built-in curling. This makes it a somewhat more conservative estimate. Again, it's a controversial thing to do. I'm not sure it's necessary to be this conservative. It seems that the code is a little bit excessively conservative in many cases. It's not necessary to do this as such a highly conservative. You end up with very, very thick pavements. And in India, that's what we do get. We tend to get very thick pavement sections because of these sort of conservative assumptions. So I don't fully agree that this is a necessary assumption. Nonetheless, I need to tell you that this is the assumption that they make. Now, what about eigenstresses? I had pointed out previously, everything we talked about was on delta TL. There is also acknowledgement that at least during the day, there is a non-linear temperature distribution. Furthermore, I believe even during the night, that is just after sunset, there is also a highly non-linear temperature distribution. So where is the consideration of the non-linearity? It's not in the temperature distribution. The temperature distribution consideration is purely taking only the linear component into account. So that means we have to look at the stress calculations. We need to look at stress and see on the stress side, is it somehow incorporating eigenstresses within the stress calculation? Although it's not explicitly talking about it when we're talking about temperature distributions. And that's what we'll talk about in the next lecture. So in today's lecture, we went through a fair amount of detail on how climate is considered. I showed you a little bit of research, which I've also done in this area. And we found that the default values recommended by IRC 58, they tend to be very conservative. So it's not even slightly conservative, it's actually very conservative. But it does recommend also to use local data to the extent possible. And I showed you some research where we tried to do exactly that using computational methods to essentially sort of check off or verify that there is indeed a lot of conservatism built inside the code. So, okay, so what I left you with was the discussion on eigenstresses and in general, how do we calculate stresses using IRC 58? And that's going to be the topic of the next lecture. So, I will see you in lecture 36 on critical stress prediction in IRC 58. Thank you.